Hello everybody, good afternoon. Before we start the video, I would just like to share with you this website for the APIs for the finite element method. So basically the idea of this is to develop modular tools for the finite element method, which include many different type of elements. So at the moment we have shell element, full integration, reduced integration solid shell element, and the full integrated solid element already available. But we are also developing more finite elements and make them available. Simultaneously, we are developing a lot of finite element templates to use with our element libraries. So you can see some of them are just free as far as you subscribe the element that you need for your FEA analysis. You can get nonlinear implicit structural dynamics analysis for free, explicit time integration scheme, buckling analysis, model analysis, multi-point constraints where you can tie different parts. So all of that for free. There are other things we also have, but we are still working on them, but they will have a small subscription fee, like return mapping procedures for plasticity, crystal plasticity, isogeometric analysis, T-splines, nerves, these kind of things, contact analysis, which is important for modeling forging, sheet metal forming, rolling, structural optimization tools as well, J-integral for fractal mechanics. Now the way it works. So if you go, for example, to the full integrated shell element, so you have some introduction to the element with some benchmark analysis and tests comparisons. We also have a pre and post processor tool where you can visualize results and build your input files to do the simulations. So you can see that this API provides the strain displacement metrics, the stiffness metrics for linear analysis, and also provides other important FEA constructs that are fundamental for nonlinear continuum mechanic analysis, like the strain stresses, rotation of the axis, internal forces, geometrical stiffness metrics, and other things. So the way it works is, so we separated the subscription for individual and academic, like PhD students, postdocs. So the idea is, if they just need to use simulation with shell elements, why should they be paying for other elements and other FEA models that they will not need? So that is the main idea of this. So you can see it's quite cheap. We also have for business subscription, so depending on the business, so 1 year £99.9 is quite, for business, is quite a cheap price, right? So solid shell as well, so very quickly, so you have a lot of benchmark tests and simulations, similar things. So we have the graphical user interface, which we developed to use these APIs, which is so basically you can import, for example, input file from Abacus and then do the boundary conditions, materials, the properties, the loadings, do everything here and run the APIs directly from this graphical user interface. Okay, you can select node sets, element sets, visualize which sets by double clicking and seeing on the tree which sets you are seeing, the boundary conditions, loading, these kind of things. You can also visualize results. So this is a full wing model run with shell elements. You can see strains, displacements, stresses, everything. Um, yeah, so please, if you are interested, so just another thing, so the site address is macinmotion.com. So we have more than 25 years experience in academia developing the finite element technology. So all of these APIs we are providing a subscription. They were extensively tested and validated, and the results are really. I can just give you a quick one for you to compare. For example, on the solid shell size, if you go, for example, here, if you see these conversion studies for this, okay, just a moment, maybe let me start with this. For this example, a twisted strip with different thickness, thin walled and thick structure. So we did run, so the API is this one, MRES API. So you can see it converges almost immediately. We compare with Abacus element, the classical one, C3D8, is very bad, but it's comprehensible because the C3D8 was not designed for bending, including bending in the 3D element. So Abacus has a better element, which is the C3D8i, the one in red. You can see it's much better behavior, but still our API still provides better results when compared with Abacus element. This is a different loading for that twist. So this is just an example to show. So we show here two of our APIs. One is the MRES, which includes bending capabilities on the element. The other is the classical 3D brick element, which is the one in black, which you can see in this example, which has a lot of bending and shear and torsion. You can see that MRES is almost perfect. AVOX C3D8i also works very well in this type of loading in this example. But you can see that C3D8 can give a very, very wrong answer, in fact, and I don't know if people are aware of this kind of situations. So this is a type of things we can provide. So just bear in mind that we are so all of these things that these finite element models for these many different problems, we have all of these implemented in Fortran. We are just basically coding this in C++, just transferring the code to C++, because C++ works better integrated with the graphical user interface, and that is and is easier to manage. Big FEA software is easier to manage software in C++ than in Fortran. So that's the reason why we are doing it. But we will soon have all of these procedures available, some for free, some for subscription, and we, of course, we provide full support on this matter. Please, if you want to reach to us, you can also go to the contact us. You have emails there at the bottom. You know now the address of the website. We'll be quite happy to discuss this with you in more detail. Thank you very much. Okay, guys, let's continue. Just some cleanup here. Let me reduce this comments. So nice, right? Okay, so I propose now that we do. The velocities, okay? Okay, can you continue? All right, so let's create here two more arrays, V, X, vector equal to zeros. Same thing, total steps. So I'm creating one array for the X components of the velocity and one for the Y components of the velocity, right?
Okay. And now the only thing we have to do is okay, why is this? Why is this red? Oh, there's a dot. Okay. You see, MATLAB is smart, isn't it? It's very smart. Okay. So let's include here the x vector counter is going to be equal to something we are going to define. Oh, not something, it's going to be equal to okay, let me just rename this thing. Let me put T and T, and now here. So it's more generic. We know this is initial one anyway, right? So then we can say Vxt here and for the Vy, right? For the Vy we can say, look guys, ideally it should be you guys doing this, but the problem is that we don't have time. For you to do this, we'll need to have maybe 2 times more session, right? Because so ideally is try to follow as best as you can, and then you will have the video lecture. Then in Brightspace, you can review better and try to do yourself, okay? In fact, you have to do yourself for the Runge-Kutta, right? So yeah, I am doing this, storing the velocities. The only thing I have to do is here, I need to update or calculate velocity, right? Let's put here velocity. Let's put a comment here, position and velocity. So the velocity equation is this one on the left, the one here, this one, right? So I just need to say Vx underscore t is going to be equal to, okay, x underscore t plus 1 minus oh, you're right. So this guy cannot be here. It needs to be before we update t minus 1, right? You agree? Should be here, right? You're going to understand why. Because this, I need to have now x underscore t minus 1, which should be before I update it here, right? Okay, and this needs to divide by 2 delta t. 2.0 times delta t. Okay, and now for the y component, same thing. So you're going to have here y of the t. So what we can do to get this organized, calculate new position. Now here, update positions for previous 10 steps, right? And these comments, they give a kind of, yeah, does it make sense? So at the moment, look at this. We store the velocity components in this array, Vx vector and Vy vector. And then we calculate velocity. Maybe I can say calculate new velocity. And then after having this new velocity, in the next iteration, that new velocity is going to be stored in that array, right? Well, I think one thing we should do before we do the period of the orbit, one thing we should do is let's plot these vectors and do some debug now, because doing too much code without debug can be a little bit dangerous. Right, so let's do this. At the end of this loop, let's plot. Plotting. Right. Is this correct? Plotting, or as another meaning? Plotting. Plotting is fine. All right, so let's use this command plot. I think it's plot, isn't it? Yeah. And then we need to have, so let's plot the position. So we are going to have x coord, y coord. Yeah. I think if we do only this, there are some options we can put there. If he plots lines or dots and lines with dots or dashed lines, but we can come back. I think I don't know if I need to have semicolon or not. I suspect maybe not. Okay. So let's run this one here. Very good. It crashed because this guy here, the CLS, I might be mistaken, but huh? CLC. Oh. Here is CLC.
No, CLS, I don't think. No, it's just CLC. That was CLC.
Okay. So if this works, officially you will be MATLAB experts. Now, from now on, you are the MATLAB experts. Okay, so let's go line by line. So our GM just checking these things. Okay, it seems okay. This is, let's check total steps. So we have total time 10, sorry, 100, delta t 0. So we must have 1000 steps, correct. This int 16 looks to be doing. In case you have doubts, I think you can just click on the link. It will do something. Maybe point you to a web page with the manual. Okay, so step, keep going, tick, 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 tick. So x0, yeah, correct. Position at perigee. Y component at perigee 0. Vx component at perigee 0. Vy component 3000 meters per second. Good. Now this is our calculation for -1. So -1 in x is this. -1 in y is -300. Okay. Hopefully this is right. This is easy stuff. So I'm just initializing arrays here. Let's go into the loop. First iteration. Let's see our time 0, beginning, right? So our epoch at the moment, because I initialize with 0, so everything is zeros, but the first one is not going to be a big difference. So counter is equal to 1, right? Yeah, equal to 1. So let's see what it did to x coord. Yeah, position 1, you have our perigee, right? Position. 50,000 kilometers is there. The y should be all zeros, yeah. Velocity Vx all zeros, but Vy, we should have the 3,000 in the first time step is there, right? Seems okay. Counter will be incremented. Look, counter should be 2 now, yeah, 2. Now I'm going to calculate my new position, x and y. So let's see. In the x direction, I have the same at the moment at this time instant, but in the y direction, it's not 0 now, it's 300 meters. Yeah, this is meters, right? Now, what is going to do next is going to calculate the new velocity components. So Vx, remember it was 0 before, right? We start to have a negative component, which makes sense. The spacecraft is going to be inside to the left a bit. So he has a component in the left direction. Vy is not changing yet. This k, how much is k? Yeah, it's okay. This k is okay. Yeah, then I update stuff and go to next iteration. So if you see now x position, but y position, we have 300 in position 2, right? The velocity x component, we have our minus 0.008 there in position 2, and Vy, yeah, seems okay to me. So let's, it didn't crash, it's good news. When it doesn't crash, it's good news. And now it's just going to plot. Okay. This is our plot. So it means our time step, total time, short. What do you think? We gave 100 seconds. Spacecraft only traveled this. Yeah. So let's see if I increase my total time. So let's multiply by 10 instead of 100, 1,000. What happens? But this is the funny part, right? We play with these things and see things. Ooh. I think we need. How much did you say in GMAT you needed?
We didn't define it.
You said days, right? 1 or 2
Yes,
days?
of course. The period is around 1.5 round.
Ooh, okay. So let me increase this by this. All right, so let's see. Oh, look at that. Amazing. Don't you guys think this thing is, don't you feel rewarding? But you know, these things happening. I feel a lot excited with these things, to be honest with you. Look how perfect this is become. Look, you can have a hint from this plot what we're going to do to detect the orbit period. We are doing a loop in time, right? So look at this. The spacecraft at the moment is here. It didn't do one period yet. So if I manage to get inside my for loop, if I detect my aircraft position is coincident with the initial position of the aircraft, what happens then? That time is going to be my period time, right?
I think for me, according to GMAT, I'm not sure what is around 2,224 seconds.
2000.
2,000. These are minutes. Minutes and in second around 1,139. No, it's way more than that.
Okay, you can give me, okay, give me your time period.
In seconds, yes.
In seconds.
139.
Okay, hold on. Let me input here. 139.
454 seconds.
This? Only this?
Yes.
Well, let's see. Oh, very good.
See.
Very good. that are some Gmatic. Definitely, central difference method is working very well, right? You can see. We can also plot velocities. Let's plot velocities. But let's plot velocity with time.
Yeah, versus time.
Versus time, right? So, in fact, we can have two plots, right? I think we can have two plots. Can we have two plots in the same plot? Maybe we can, okay? So if I now just, okay.
Not V-points, right? We don't have any VX.
Let's put plot position, okay? Now let's put here a comment, plot. You want to plot Vx?
I'm saying VX is 0, yes. V-point.
We can plot both. Plot, okay, let's start with Vx. Plot Vx with time. So in that case, we need to do plot, right? So let me, what's the name of the array we use? Vx vector, right? So we, oh no, first needs to be time. So time is our epoch in the x-axis, and vertical axis is going to be Vx vector. Now, let me use, okay, options. Okay, for example, line spec. I want to know what are the line spec options. So if I click on this link, what happens? Let me see. Nothing happened. Nothing happens. Come on, MATLAB. Oh, maybe it's here. Okay. No, but there's, it changes to a hand, right? A link. So if I click, she'll give some. Oh, okay. The only thing is just, oh, okay, okay. Oh, you're right. Okay. Is marker. Or I can put line style, right, as well. Oh, let's put marker. So marker. Okay, I had an idea if I put something like this. Anyway, let's see. Oh. I can see Cheyenne is happy.
Just you mentioned the magnitude of the spacecraft velocity versus time. So does this mean Vx square root of Vx squared plus Vy squared? The spacecraft
Square root of that. Yeah. This is only the x component, right? Okay, so this, I think these are circles, all circles, right? Let me see. If you zoom in this thing. Oh, okay. It doesn't matter. So it's just oh, okay. It's just the road above the other plot because I don't have any other plot. So I think we need to put here hold on, right? Something like that. If I put this, it might hold on that plot and not replace it. Yeah. Oh, the other one is that tiny thing. No, we don't want to do that. No. Okay, so how can we have two plots, two windows, one for each plot? Oh, I don't remember. I think, okay, I think if you do this, figure position equal to this. And then if you store this in another variable, let's see if it works. Figure Vx equal to this. In fact, let me change this to I don't like the circles, they becomes too thick. Now I have this. Now I think if I just do figure position, oh, so can I do this?
Yeah.
But then I will end up in the same thing, right? I suspect. We'll see.
But you want both to be in the same plot.
No, different plots. I suspect it's going to be the same thing. Yeah. It works, but I don't have different plots. Okay, anyway, it's okay. Okay, so let's leave it like this. So what you can do, you just comment the one you don't want to plot. What? It's a bit strange. Why is it plotting this now? Okay, anyway, forget this. Okay. Right. So guys, let's focus then on the loop. So one way we can do this is detect okay, so I have one strategy. So I'm going to switch to the iPad now. This thing is saving, isn't it? Is this saving? Yes. Okay, so let me switch this thing, share the screen here in the iPad, because I'm going to define a strategy for you. Okay, guys, so let's agree on one thing. Take the lecture today as a lab, computer lab, okay? You don't mind, right? I'm quite sure you don't mind because I'm helping you in your assignment, in fact. Yes.
And regarding the code, Roach could talk. I remember in last meeting stuff, but there is not a straightforward. There is no specific for Windows step like the one that you did here. It was some modified approach that we had to apply it by doing some points. I remember it had some points there drawing the line.
You need to do what we did here with central difference method. Replace those Roche-Coulter things in the differential equation, and then you will get similar like the ones in central difference method.
You mean those X, Y things that you put there? I remember, rather than R for Windows, we have to put the one to which bits of the code, for example, that's different from the one when we want to insert a new one, which are things that should be changed.
Well, that's your job. That's your job in the assignment. I'm doing already a lot here for your assignment.
No, I'm not saying.
No, that is your job in the assignment. You need to figure out how to do it. Yeah. But I will say you have 90% of information. Yeah. 90%. I mean, for the Roche-Coulter and MATLAB, yeah. But I'm not talking about the GMAT thing you were asked to do, right? Okay, so let's define a strategy here. So we have a orbit. Perfect elliptical orbit. And then we are going to have our position vector. I'm going to put it. So this is the periapsis, right? Or perigee, or perigee, right? It's perigee. Perigee. This is going to be your R, okay? So your aircraft starts from here, right? Imagine your aircraft is now here. So this is going to be your initial position, R0. This is going to be your RT. We can calculate this angle, right? I might have to close now a little bit. This third.
This is what velocity. But not.
You are going to see. With orbit, you have aircraft. In this sketch I have just put here, you have aircraft in two positions. One is the initial position, perigee, okay? The other is a generic position T. This is position vector, right? At that position, RT, this is the initial one. You have both. So how can you calculate this angle? Theta. Well, look at this. You have, if you do the dot product between these two vectors, you are going to have RT dot product with R0 is going to be equal to norm of RT, which you can calculate in MATLAB, times norm of R0, you can also calculate, times cosine of theta, right? Hmm? No, the angle is between these two vectors, R0 and RT. I want to calculate this angle, right?
Oh, so it's different from true anomaly.
No, this is a true anomaly. Angle.
Because I heard that 0 is at perigee and at 180 is at apogee.
Yeah. But this theta, so this RT is a generic, is a position vector for a generic time t.
Oh, okay.
Okay. It doesn't have to be on. Yeah, if it is at apogee, yes, that angle will be 140, 180, right? But I want to calculate this angle for a generic t. Because in our loop, we have a loop in t. We need to calculate this angle for every single time step, right? So if we do this, look at this. My vector RT will have a component, this x underscore t, y underscore t. My vector R0 will have x underscore 0, y underscore 0. This one is going to be square root of x t squared plus y underscore t squared, right? This will multiply by another square root of x underscore 0 squared plus y underscore 0 squared, right? And this will multiply by cos theta. Okay? So if you want, we can say that x underscore t times x0 plus y underscore t times y0 dividing by square root t squared plus y t squared times square root x 0 squared plus y 0 squared equal to cosine of theta. Okay? And why is this good to do that? Because look at this. If my spacecraft, if you consider different positions for the spacecraft, this and then this, yeah? Huh? So if you, for every time step, if you do this cos theta equation, when this cos theta is equal to 1, it means what? 1 is when angle theta is equal to 0, right? So theta goes. The angle theta is going to increase 90 degrees, right? Theta. Then apogee 180. Then this position here 270, 360. And if you do cosine of 360, equal to 1. So you just need to monitor cosine of theta. When it reaches 1, you say, okay, that t in my loop is my period. You agree? Okay, let's do that in MATLAB. Yeah, let's do that bit in MATLAB. And then you have a full package for free. We can say this is open source software. Right, so let me share this figure again. So we can switch to MATLAB. Okay. Switch here. Let me just put that figure. Mhm. Okay. Right. Share. Okay. So you agree with me with this? So I suggest we do, yeah, let's just do this equation here. So let me define a tolerance, a very tiny number. Tolerance equal to 1.0 E minus 10, for example. Okay, this will be our stopping criteria. Right, let's calculate. Okay, let me define another thing. No, it's okay. Okay, time, no, orbit, time, period. Okay, define this variable. I'm going to put to 0 so we don't have strange numbers. And now I'm going to calculate here. So put some comments. Calculate cos theta. through anomaly. Yeah. Calculate cos theta through anomaly. Okay. So let's do this dot product we have there. So let me put here cos theta. Is variable cos theta. So let's do cos theta. Is going to be equal to, okay, numerator. Oh, okay, we need to avoid this guy to stop at the very beginning, right? Okay, anyway, let's calculate this thing. X underscore t times x underscore 0 plus y underscore t times y underscore 0. This will divide square root of x underscore t times x underscore t plus y underscore t times y underscore t times square root x underscore 0 times x underscore 0 plus y underscore 0 times y underscore 0. Right? This is my cos theta. Okay, now we need to avoid this thing stopping at the very beginning, because at the very beginning cos theta is going to be 1. Isn't it?
Start it from zero.
Hmm?
If you start it from zero, what to go around?
Yeah, that's what we are doing, right? We are starting from 0. Let me think what we can do here. Oh, I know what we can do. So we can start, okay, cos theta is going to be 1, right, at the beginning, right? And then, in theory, yeah, in theory here is going to be smaller than 1, right? So what we can do is we can put an if here saying, okay, let's put, yeah, we need to create another variable. Cos theta initial 1.0. Now what we shall say is something like this. Let's put a condition here. If cos theta is greater yeah, greater than cos theta in E. If it is greater than that, and this cos theta in E, I'm going to do, say, is going to be equal to this plus a toler, plus the tolerance, just to make sure that doesn't happen. But anyway, we need to debug this and check better. But so if it is greater, it means we are in this lower bit, right, of the orbit, right, is when cos theta starts increasing, right? Because here, oh, okay, I need to put ABS. No, not ABS. Yes, no, this is correct, because if it goes between 90 degrees and 180, cos will be negative, so it will never be higher. That's correct. I think this should be fine. So anyway, you can think better in your assignment. But you can put it in a different way, but let me see if this works. So once it becomes to be higher than this, what it's going to mean is then, yeah, what I'm going to do is now check if, another if, absolute value between cos theta minus 1, right? If this is lower, equal the tolerance, it means the spacecraft reaches the perigee again, right? So what you can do, you can put a comment here and say, okay, if it comes inside this, it can say, the spacecraft reached perigee. And then what you do is you say your orbit time period, variable orbit time period is going to be equal to t, and you can get out of the loop, you can do a break. Else, if you didn't reach perigee, what you have to do is you need to update your cos theta in E. Your cos theta in E is going to be equal to your cos theta. And ifs and ifs. I'm curious. Okay, so let's do one thing. Let's test this thing, but before that, I'm going to remove here Cheyenne's time period. I'm going to put one more zero in front, okay? To see if he's getting out of the loop and finding the orbit time period, okay? So let's do this slowly. So let me start to run to here. Okay. Now, run here and go online. So cos theta is 1.0, cos theta in E. Don't forget I gave the tolerance is tiny, right? So it should not get into this if, but we'll see if I do step, it didn't get in, correct. That's perfect. It goes to the next iteration. Ding, ding, ding. So that's all of that. So cos theta should start to reduce. Not getting in because I updated this guy here. Oh, I didn't update. Oh, wow, that's one thing I need to do. I need to put the else here. Yeah, I need to put the else here. And do this cos theta in E equal to cos theta. Okay, let me just. So first iteration, we are back in first iteration. It goes into this else, cos theta was updated. Second iteration, updates cos theta again, so it's fine. So what you can do is, okay. Okay, I can put a breakpoint here and click continue. So if it gets inside this if, it should stop at this breakpoint, right? Oh, it did. How much is time step t? Is a little bit smaller than yours. A little bit smaller than yours, isn't it? Well, it did stop. So what is going to happen now? I'm going to continue step by step. It's going to find this break, it's going to get out of the loop. So if you count the number of time steps it did, the counter is 1,112,669 steps, iterations in this loop. And this should correspond. So your orbit time period is now that time. It should get out of the for loop and it should plot. Perfect. It did plot the entire orbit. So our, yeah.
But the period that you mentioned, I think for your one is right, for me is around 31 minutes higher. You know, I did a little bit 31 minutes for me. This is lower in seconds.
So if you convert that seconds to hours, how many hours you have for the orbits?
Hours. Okay.
You need to divide by 3,600, right? Divide that by 3,600. You should get hours, right? Are you following? I think. Very quiet. But you're following, right?
Yeah.
If not, it's running.
It will be 3.87, around 4 hours, 3.87 hours.
Yeah. So let me see this one, Omen. So this one. Oh. Oh, I have it here. So it's 1, 1, 1, 2. 7.
Sorry, 38.7.
38 hours.
38.7. Yeah, that's why I said it's around 1 year.
38 hours or 309 hours.
Just divided by 3,600. The second.
Oh, hold on. Okay.
And it's 1 year.
Okay, I have it wrong here. Okay. 1, 1, 1, 2, 7. I have 30 hours, 0.9, almost 31 hours.
For me, it's 38.5. But use the GMAT difference probably. And also, you are not the watch group.
That's a very good point. That's exactly what I was about to say. So, Rushcutter, because Gmat I think uses Rushcutter, right? Okay. Right. So basically, guys, that's it for today. I think. Yeah.
This one's good, it's more accurate.
Rushcutter is more accurate, but what you can do, you can decrease the delta t. Hold on. Oh yeah, I did put one more zero here. Okay, I remember. Okay. Okay. Yeah, what I was saying is that if you want to make the central difference more accurate, instead you reduce delta t. Let's put instead of 0.1 second, 0.01. It will do much more iterations, right? Take more time to run. So let's put a breakpoint here. Look, it's taking a lot of, oh, it did run. Oh yeah, same. 111,270 seconds, which gives 30.9 hours. Okay, you need to double check. And that's why this thing is good, because why? You have GMAT results. The Excel, you have only the orbit, you don't have the time orbit time period. But then central difference method, you have orbit time period. And now we are going to do Rushcutter, right? Same thing for Rushcutter. You are going to have also orbit time period. These numbers, they should be a bit closer, I think. Something might not be right, either on this one we did or on GMAT.
So that should be more closer to the GMAT.
Either this more closer to GMAT or GMAT closer to, it can be the input parameters you put something that is a bit strange, right?
For me right now, the orbital trajectory matched exactly. So I want validation for that case. The trajectory is matched.
Okay, so homework, central difference, the orbit trajectory, put in the same plots you did put with the Excel and with GMAT. First thing, to see if the orbit matches well.
Okay.
This one, yeah?
Because that match.
That match, okay. So try to put this one as well, match, and then Rushcutter, do the same thing. Put everything in the same plot. Of course, the orbits, they all need to match each other, right? Okay? If some of them does not match, it means there's some error there somewhere. You need to find out.
Yes. So the Excel isn't just for task one, or we compare the Excel with this one as well.
I don't remember if I asked the Excel in the brief. Do I?
Yes. Part B, I said.
I asked that.
Yes, you said either MATLAB or Excel. Even if you use Excel, you ask in the beginning to provide it.
No, but for Rushcutter, I asked it not.
No. I'm talking about analytical. He's talking about analytical.
Analytical, yes, but when I asked the Rushcutter is for in MATLAB. MATLAB, yeah. Yeah, do that. It's quite interesting. That's when you learn most. If one of the methods you use, the orbit is not coincident with the others, then you need to go deep and investigate what is wrong with that method. But in theory, they should all match. Okay?
And regarding velocity, sorry, I noticed I used V-body for MATLAB. The plus
I use what?
V-body, just velocity component in the y direction. I didn't consider Vx. Apparently there is some option called Vmax.
V magnitude.
V magnitude, yeah.
I didn't use that.
V magnitude is the norm, is the norm of that vector, the velocity vector, right?
And when I did V
Is the square root with the component squared.
it wasn't that much different from VY.
It was not.
For me, it's V1.
It wasn't that much different.
Anyway, you guys you have velocities here now as well. Can be a double check, this one, right? Yeah.
This one that we did was Vx. We didn't use magnitude.
No, it just.
Oh, but you can very quickly do that, right? Okay, let me bring back the time here to 0.1. Now here, what you can do is, look guys, what you can do is, you add another one, you can just copy paste. Oh, this is a, oh, I should not. So plot Vy with time, epoch, you just need to do this, right? And then if you run again, you can leave this here because you were only going to do for one orbit. So even your velocity, this velocity profile with time is going to be only for one orbit, right? So if you run this thing, yeah, this is the right thing. This is Vy, right? Vy. Yeah, look, you can confirm some points. Horizontal axis is time, don't forget. Time 0, your Vy is 3000 meters per second, right? And then it decreases. So this point here is the apogee, right? And then it starts increasing again, reaching 3000 again when it completes the orbit, right? And keep, then the next time it keeps getting this profile.
And for magnitude, you have to do the square root of both of them. Okay.
Do you know what you can do? Sorry. Sorry. You can put in the same plot Vx and Vy, and in that case you need to put here hold on, right? Right? So if you do that and run, yeah, look, this is the power of MATLAB. Yeah. So the one in orange is the Vy you recognize. The one in blue is Vx, right? At the beginning, perigee, Vx is 0. Now you can calculate the magnitude of the velocity. You just do the square root of the Vx squared plus Vy squared. And then you can plot here another one, which is the magnitude. We can do that quickly if you want. Look, you just do this, guys. Look at this. V underscore magnitude. Create a new array. I think we still have a little bit of time, yeah. V magnitude. You create another array, zeros. And now here, you just do something like this. V magnitude in this position given by the counter is going to be equal to square root of Vx underscore t times Vx underscore t plus Vy underscore t times Vy underscore t. Right? And then here at the bottom, you do hold on again. And then you can do plot V magnitude. Then you have a plot epoch V magnitude, right? Okay, let's run this thing. Now you should have ooh. You can put a legend in these curves to identify the curves. So the magnitude is one in yellow.
But you said there is no difference.
Yeah, there's not much.
Alright.
How can you explain the red, the yellow one?
The yellow one, how?
How can I explain?
How do you was the physics?
What do you mean the physics? It's the total velocity of the spacecraft. Don't forget, spacecraft is in the XY plane, right? Well, I can tell you how I explain. You know, if you look at this figure, at perigee here, right? You have only vertical component, right? Look, this is perigee, right? So the magnitude is the same as the Vy, right? Which is correct. But then what is happening? When it's moving, the velocity is tangent to this trajectory in blue, right? Imagine a tangent. What is going to happen is that tangent, at the perigee, that tangent is a vertical line. But then once it's moving in the orbit, the vertical component is being reduced and the horizontal component is being increased, right? That's what you see here. Vertical component, you need to think on the absolute value of this is velocity. So absolute value. So why you need to think absolute value? Because when you calculate magnitude, we squared, right? Where is it? It's here. When we calculate magnitude, we squared Vx. So this minus here, it doesn't matter for the magnitude because minus times minus becomes plus, right? So you need to look at the absolute value. So what happens is you are adding these two components always. So the yellow is the result of the square root of these two components squared and added together, right? So the vertical component, when you move in the orbit, the vertical component is decreasing. Once it reaches this point here somewhere, the vertical component is 0. But then after this point here, it starts increasing again and reaching the maximum at the apogee. Minus 3000 is this point here, right? In the plot, minus 3000. And then at this point, the x component at the apogee should be 0. Well, you can see here, right? This is somewhere at this point here. It's close to 0, right? Yeah? The x component. And then from the apogee, when it goes, what is going to happen is the vertical component of velocity is going to be decreasing, while the horizontal component is going to be increasing. That's what you see here. Horizontal component is going to be increasing, is this one in blue, while the one in orange, it's going to decrease from 3000, it's going to decrease. But anyway, you can in GMAT plot the magnitude, right? You can plot that in GMAT. So plot and compare with this.
But he's saying that the Vy,
Yeah, for 50,000, like because I didn't plot the graph, like when I got the values for 50,000, I got same as Vy, which I got 2.9999.
Yeah, 50,000 is correct because you mean at perigee, right? Yeah, that's what we get here. The yellow is coincident with the red at the perigee, right? You have same. And it should be the same, huh?
that one, yeah, that's not the problem. He's saying that the trend was like the Vy, the trend of, right now, the trend of the yellow color is not the same as the blue color, right? The red color. But Vy is quite different than the Vmax, but he's not observing that in the Gmax.
You need to double check, I don't know.
No, I'm saying from GMAT, you can extract the magnitude and plot it with time. You
Yeah.
can do that.
Okay.
Yes, but we said it's the same as Vy.
No, I meant that the start is the same. I haven't plotted the graph. Oh, you did? No, I didn't.
after you do it.
Okay, as we see here.
And sorry for the assignment, do you recommend to do, right now you have three things here, you explain it very well about having these three together. In the assignment, you just asked for the velocity magnitude. Should we just put this orange color one, or do you want us to put these three together and somehow?
You can put 3. I asked only the magnitude. That is the minimum thing you need to show. But if you want, you can show the x component, y component. Yeah. In fact, this is quite a nice analysis. Look, the magnitude, there is also a variation, right? The problem is the scale of this axis. Let me see if I can change that. So let me see. Oh, I think it's this thing, right? Oh, this is the ticks. Okay. Where do I define the... Oh, the limits. Okay. Might be this, right? Or not? X limit. Y limit. Maybe not. Okay, let me try the Y limit. So let me put the Y limit between, so let me take this minus, go away, and put here, let's say, 2. Yeah, look at that. Look what I did, guys. You see the magnitude is also changing, of course. But because the axis limits were very high, you could not see very well the variation on the yellow line, but yeah, but it's changing less. Yeah, it's changing less. Well, you can check these points, right? Oh, interesting. I'm going beyond my MATLAB skills now. Anyway, guys, you have. I hope this central difference method is helpful, and it will be helpful for your assignment for Brunschkutte. So I will provide this thing in white space. Okay. So you need just now basically to adapt the Brunschkutte to this, right? And put everything together with GMAT, and we can talk. When is deadline for this thing?
No.
Yeah, I still have. Today is what, 28, right?
Yes.
This month is 31 days. Anyway, almost more than 2 weeks.
So you don't have page limit. What do you, how want to see?
You don't want to write a thesis, right? I didn't put page limit. Okay. Yeah, just do a proper report. Okay. Imagine you guys need to train yourself for industry as well. Okay. So you're going to have many projects like this in industry, right? You are going to work in a team, but at the end of the day, you're going to need to produce a report to your line manager, right? You are going to need to present your work. So having a report that explains everything you did is a good thing. Yeah. So don't put just a plot without any comments, without any discussion. Try to provide a discussion, okay? What you did, why you did, what the meaning of the variables, yeah? The MATLAB implementation steps, if you want to give some comments on there as well. Okay, your inputs in GMAT, how you did that.
You want the inputs in GMAT, you want to know how we did the GMAT.
Yeah, give some description. Don't put just GMAT screenshots, that's it, right? Try to explain how you model in GMAT, right? You said, for example, use a Cartesian instead of the Kepler. Well, explain that. Explain your inputs. If you use the Kepler things, explain what Kepler inputs you did, assumptions you made. Do a proper report, right? So that the person that is reading the report, imagine that person is your line manager. You want your line manager to have a good idea of the work you have done, right? With all the details, things you have done, right? Imagine I am your line manager. That's it. Produce a report in that basis, okay?
And for the prosecutor, they want us to explain the theory
Yeah, the theory is just those equations. You need to put equations there, right? And need to replace those equations in the differential equation of the orbit, right? Those steps, they should be in the report, yeah? Okay? Okay, guys. Let's stop here. What time is it? Oh, 10 minutes. Perfect timing, amazing. See you guys next week, okay?
Imagine how we can
Let's say you just.
This is not wrong, this is not right, because it can't be this. But you have to subtract the time from here to there. You should just see how long time it takes.